OCR A-level physics, and this video is about gravity and orbits. So what is a gravitational field? A gravitational field is a region of space where masses experience forces. While we're here, an electric field is a region of space where charges experience forces. Magnetic fields are a bit more tricky because there's a few things that experience forces, but gravitational field, if a mass is experiencing a force because it's in that field, it's a gravitational field. And if you let go of a ball, it experiences a force and it falls to the earth, it accelerates because it's in a field. Now, the gravitational field strength is defined as the force per unit mass. Now, our unit for mass is the kilogram, so the force per kilogram, newtons per kilogram, little g. Now, as we have F equals ma, so A equals F over m, then it's actually the same value as the acceleration due to gravity, and we use the same symbol. So little g is gravitational field strength in newtons per kilogram, and it is also the acceleration due to gravity, which is 9.81 meters per second squared. It's the same symbol. They are equivalent units. If you boiled them down to the base units, they would be the same. In fact, meters per second squared is base units. Now, we can represent fields. This is either electric fields or gravitational fields or magnetic fields by drawing field lines. And looking at these field lines, I can tell that that is a uniform field because the lines are evenly spaced and they are straight lines. And that tells me that the field strength is the same everywhere. The gravitational field close to the Earth is approximately uniform. We can consider it to be a uniform field. It's 9.81 newtons per kilogram everywhere close to the Earth. However, as we move away from the Earth, the field gets weaker. And we can see that looking on this diagram. And I know that because the field lines are getting further apart. Okay, the strength of the field is actually the number of lines per unit area. If you think of it in 3 dimensions, yes, the number of lines that would go through. These lines don't exist, by the way. They're just a way of representing the field. But I can tell that this is a non-uniform field. The arrows show the direction of the field. Now, with gravitational fields, it's always attractive. With electric fields and magnetic fields, it's a bit different. But remember, the arrows show the direction of the field. This guy, Johannes Kepler, I'm going to talk a bit more about him later. Now, he figured out the rules governing the orbit of planets and the orbit of the moon around the Earth, but we didn't know why they stayed in orbit. Why do planets go round the sun? And in fact, for a while, people thought that everything went round the Earth. And the best guess at the time was that it was angels carrying them around, or they were on celestial spheres or whatever. Now, this bloke, Isaac Newton, very clever bloke, realized that the force that keeps the moon in orbit around the Earth and the planets around the sun was the same force that pulls an apple when you let go of an apple and it is pulled towards the Earth, and that is the same force that provides the centripetal force which keeps the moon going in orbit around the Earth. So that was a brilliant thing to realize, and by looking at Kepler's laws and the work of people like Galileo and the motion of the moon, we come up with Newton's universal law of gravitation. All masses attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of their separation. And what I've just said there is this equation here. It's that equation in words. All masses attract each other, okay? And the force is proportional to the product of their masses, so that's m1, m2, and inversely proportional to the square of their separation, center to center. Now, you can't actually work out the size of any forces because we don't know the constant in that equation. And it was like 100 years later that Henry Cavendish found a value by doing an experiment with some big lead balls, and he actually measured the force between them using something called a torsion balance, and he came up with a value for big G, and big G is the constant in this equation, and so we get F equals G m1 m2 over r squared. So here's a little sum for you to do. Have a go at it. Pause the video. Don't be lazy. The answer in 3, 2, 1 is... There you go. Okay. Interestingly, this is what actually Cavendish used in his experiment. Yeah, the masses of the balls that he used. And look how tiny the force is. Okay, it's like 0.2 millionths of a Newton. Tiny force. Here's another one for you to have a go at. Yeah, large mass, small mass. Calculate big M. Well, there you go. I've worked out big M, and there it is. It's about 6 times 10 to the 24. Maybe you've realized what you've just done here is you've worked out the mass of the Earth. Yes, because the force on a kilogram, 9.81 newtons per kilogram. It was said that when Cavendish worked out a value for big G, we could work out the mass of the Earth. It was said that he weighed the Earth. We've known what the radius of the Earth is for a long time. A guy called Eratosthenes figured that out. But now we can actually work out the mass of the Earth. And it turned out that it was a lot heavier than we thought it was, because the Earth isn't all made of rock. It's got like this iron core, iron and nickel core, hasn't it? A metal core. Now, the force acting on a mass, M. So we have F equals G m1 m2. So let's have big M and little m. And so the force per unit mass is little g is F over m. We've said that. That's our gravitational field strength. So looking at the equation, we get little g equals gm over r squared. G times big M over r squared. So that is the gravitational field due to the Earth or any other big planet or celestial body. Little g is gm over r squared. Notice that it follows what we call an inverse square law with distance. Inverse square, so there's inverse, like 1 over, and square because it's squared. And a graph of g against distance from the center of the Earth would look like this. Inverse square, as in if we go twice the distance, so on this graph, if we go twice the distance, the field strength is a quarter. If we go 3 times the distance, then the field strength is a ninth, etc. It's an inverse square law. You don't need to know what happens inside the Earth, okay? I'll tell you anyway. If the Earth was a uniform sphere, then it would just be a straight line like that, but it's not a uniform sphere because you've got different bits inside the Earth, the inner core, outer core, etc. So it's a bit more stepped. But anyway, you don't need to know that. Inverse square law for little g. Okay, now, if we fire a cannonball, do this in your back garden. If we fire a cannonball horizontally, then it follows a parabolic path and it falls to Earth. You did projectiles in the first year, okay? Now, if we fire our cannonball horizontally fast enough, if we give it enough velocity, then ignoring air resistance, it's going to go into orbit. It will continually fall towards the Earth, but because the Earth is curved, it will never hit it. If it's traveling fast enough, it would have to be something like 8 kilometers a second. But if it was traveling fast enough, it would continually fall towards the Earth. Following the curvature of the Earth, it would go into orbit, ignoring air resistance. So we can put a satellite in a circular orbit around the Earth any radius you want. Okay, any radius you like. There are certain conditions though. The center of the orbit has to be the center of the Earth. And at any particular radius, it has to have a certain velocity. Okay, generally, the bigger the radius, then the slower it goes. The closer to the Earth it is, the faster it has to be going. Okay, so those are two conditions for an orbit. But the point is, any radius you like, you can put an object in orbit. Look at this equation. This is how you would work out the velocity. Always start with F equals ma. So F is gmm over r squared equals mv squared over r, remembering our circular motion equations. And we do a bit of cancelling. V equals root gm over r. So that's how you would work out the velocity for any radius. Okay, here's a question for you to do for a close orbit. An orbit which is just above the atmosphere. To get above the atmosphere, you only have to go up about 100 kilometers. Yeah, if you could drive your car upwards, it would only take you about an hour to get into space. Yes. Anyway, have a go at that question, and the answer is in 3, 2, 1. There you go. Velocity about 7,920 meters per second. I said about 8 kilometers per second. And then the period, I've just done circumference over velocity, 84 minutes. Around the world in 84 minutes. This is a close orbit. A close orbit that goes above the poles is very useful because then you can actually, as the Earth rotates underneath the orbit, you can look at all the different bits on the Earth. Very good for spying on people, I have found. Great for spying. Now, here's another very useful orbit that you need to know, and it's the geostationary orbit. Okay, stationary, geostationary, it's stationary relative to the same point on the surface of the Earth. So your satellite dish on your roof is always pointing at the satellite because relative to your house, the satellite doesn't move. Very useful for communications and for GPS. Yeah, the maths of it now there's another condition for GPS satellites. Two conditions actually. To be geostationary, it has to be above the equator, and if you look at this animation, that should be obvious why. And it must have a period of 24 hours. Yes, a sidereal day, actually 23 hours and 56 minutes, but don't worry about that. A period of 24 hours, and that is only possible at a certain radius, and therefore it must have a certain velocity. This place where all the geostationary satellites are gets very, very busy, lots of signals interfering with each other as well. The maths of it, again, we start with F equals ma. So gmm over r squared. This time I'm going to do m omega squared r. Omega squared r for acceleration. And so omega squared equals gm over r cubed. Omega is 2 pi over t, so square that. And I get this expression, t squared over r cubed equals that. Why have I gone to the trouble of doing that? You'll see in a couple of slides. What you can do now to find r is, we know t is 24 hours. And then when you know t, you can work out the velocity, can't you? No, you can work out, knowing r, we can find a value for v, which is from the equation we had on the last slide. Kepler's 3 laws of planetary motion. What are them? Not particularly interested in the first 2, but the specification says that you should know them. The orbit of planets around the Sun are elliptical, with the Sun at one of the foci. Planets sweep out equal areas in equal amounts of time, and then this t squared over r cubed equals a constant. Who's Kepler? Well, Kepler, he used lots of observations. A guy called Tycho Brahe very interesting character, did lots and lots of observations, took lots and lots of data, and Kepler was a very good mathematician, and he came up with these laws using that data. Kepler's first law. So the orbits of planets around the sun are elliptical. Sometimes you see very misleading diagrams, like, there's the sun and there's a planet going around the sun. It's nowhere near that eccentric. Okay, I mean, the Earth goes around the sun. At its closest, it's 147 million kilometers, which is in December. And at its furthest, it's 153 million kilometers, which is in June. So looking at those numbers, it's not very elliptical, is it? I mean, the average is 150 million kilometers. And later on, you're going to need to know, we call that 1 astronomical unit. It's the average distance between the Earth and the sun. Okay, 1 astronomical unit. Nevertheless, Kepler's first law, an ellipse has 2 foci, and the sun is at one of them, and the planet is at orbiting around this foci in an ellipse. Kepler's second law, planets sweep out equal areas in the same amount of time. Basically, when the planet is closer to the sun, it's traveling faster. Yes, when it's further away from the sun, it's traveling slower. And basically, as I said, in the same amount of time, these areas are the same. And that's Kepler's second law. Kepler's third law, okay, t squared over r cubed equals a constant. Or you can write it as t squared is proportional to r cubed. It's the same thing. And if you've been paying attention, as I said a few slides ago, when we were talking about geostationary satellites, I actually derived that equation. You need to be able to derive it, by the way. Yeah, start with F equals ma and come up with that equation. Yes, you need to be able to do that. I've given you some data about planets here. If for yourself, if you want to confirm that, so you need the orbital period, so that's t, and you need the orbital radius, which is somewhere in this orbital radius. Where is it? Distance from the sun. That'll do. And for yourself, you work out t squared over r cubed, and you should get the same number. If you did it for another solar system, then the constant would be different, because big M would be different, wouldn't it? Yeah. So your 4 pi squared over GM would be different. Here's a sum for you to do. Nice little exam question to finish off the video. Have a read. Okay. And the answer is, there you go. So the way I've done it, t squared over r cubed equals a constant. So using data for the Earth, I've worked it out. And so I know the constant, so now I can work out r, and that's 415 million kilometers, which is, if you look on that table, is somewhere between Mars and Jupiter. It's in the asteroid belt. And so this dwarf planet is actually called Ceres, and it's in the asteroid belt.